Hi, this is Chuck, and in this particular video, we are going to be taking a look at mechanical vibrations. And the mechanical vibrations in this case are going to involve a spring. And this spring is going to be within a system where there are no external forces acting on it, for example, friction and things of that nature. And it's also undamped. Now, as we start considering applications, we need to be familiar with some terminology. One of those terms is a damped versus an undamped system. The idea is there some fluid or something that acts upon the system that absorbs part of the energy and reduces the spring within the system? For example, let's say that you have, over here on the far right-hand side, a spring, and let's put this in a zero gravity situation like this, with a mass hanging on it. If you pull this thing down and release it, it's obviously going to bounce up and down and up and down and up and down. If there is no friction within the materials within the spring, if there's no gravity, if there's no external force acting on this thing could continue forever. You are familiar very likely with a car, and in a car there are things called shock absorbers. The idea of a shock absorber is you have two pieces, one that slides inside of the other. And inside of this there's a rod with a piston. Part of this shock absorber attaches to the frame of the car. The other part attaches to the control arm, which is down at the bottom where the wheel attaches. If you were to just hit a bump without a shock absorber, the car does have springs on it, and that car, because of hitting that bump, would bounce up and down and up and down and up and down for a considerable period of time before it stops bouncing around. What a shock absorber does is, as you hit a bump, it depresses part of the shock into a cylinder that's filled with fluid, and it's very difficult to move this piston through that fluid. But some of the fluid eventually works its way around. And then as, for example, you hit a bump, the car's tire drops down and it comes back up in a pothole. What's going to happen is the piston's going to want to move one direction first. Then, because of the spring wanting to restore the car to its original position, it's going to want to move this piston the other way. Well, as the liquid was forced to the far side, when this piston presses that liquid, it absorbs a lot of the energy in the bounce. Then as this piston wants to move back this way, once again, it has to press the fluid back up this way. And with this moving the fluid back and forth, a lot of energy is absorbed. Okay, and it literally absorbs the shock, just like the term shock absorber implies. Okay, so there are a lot of situations where you're going to have systems with some type of a damper in it. And a damper just being something like we just talked about, that it takes a lot of the energy out, causes the spring and the mass to return to a natural position, or actually an equilibrium position, and keeps things from vibrating, bouncing, things like that. As a lot of you are probably going into engineering, there are all kinds of situations where there are vibrations. This first system we're going to look at is what is called a free system. That means there are no external forces that are going to subtract energy, for example, friction and things of that nature, and it's also an undamped system. These two components, some outside force acting on it as well as a damper acting on it, will affect how the system behaves. For right now, we're going to not include those, get some of the mathematics down in modeling this system, and then in future videos we'll take a look at how does introducing external forces and damping impact the model, as well as actually impact the shock absorber or whatever it is we're going to be talking about. Okay, you should have seen some of this in physics, so I'm going to go through this a little more quickly than I would have gone through it had you not had a physics course at any point up to this time. But what's going to be going on here is we're going to be considering a spring, as you can see to the far right over here. And this spring is hanging in what's called its natural position. You just hook it on, and it's just the weight of the spring. And with just the weight of the spring, it's going to reach down some amount, but it's not going to really stretch that much. Okay. The natural position is indicated with a lowercase l for length. Now, you come along and you attach something to the bottom of the spring, some mass of some sort. And what you wind up with now is a situation like what we have to the right over here. The spring is going to elongate some because the mass is going to pull the spring down. The amount that it elongates, this capital L, is going to be the distance from what the natural position was down to where the new center of gravity is. Okay, so we're going to be measuring capital L, the elongation, as just being the additional length that's achieved by attaching the mass to the spring. As we work through these problems, you're going to need to be mindful of several things. One of those items that's listed up here in the upper right-hand corner is, as we look at these systems where something is hanging, positive is going to be in a downward direction. Moving upward is going to be in a negative direction. Okay, and this is with reference to gravity, either moving in the direction of gravity or in opposition to gravity. Positive being moving in the direction of gravity. A second thing to be mindful of is when you get out there in the real world, not everything's metric. So we need to be mindful that there are two systems out there, the imperial system, which is feet, pounds, gallons, and the metric system, okay, which is going to be meters, grams, and liters. Okay. If we are working in the metric system measures whatever it is you're hanging on the spring in terms of a mass. So there's no conversion that's required there. If, however, you're working with the imperial system, for example, you're given the weight, not the mass, but the weight of the item, you're going to need to convert this to a mass. If you'll recall, weight is equal to mass times gravity, which means that the mass is computed by taking the weight, dividing it by the gravity, which is what you see right here. Okay, so we've determined what a positive direction is. Needed to be careful about the difference between weight and mass. Another thing to be mindful of is, especially in the empirical system, if you're given some of your measurements in inches and others in feet, you're going to need to be careful to convert everything to feet. Well, why feet? Well, this brings us to yet another facet to keep in mind. Okay, acceleration due to gravity. You probably or should be familiar with its 32 feet per second squared. Oh, there are those units of feet. It's also 9.8 meters per second squared. Aha, the length there is going to be in meters. Keep in mind that these are approximations. These are not the exact constants for gravitational acceleration, but they're good enough that they're going to work for us. Okay, the first thing we want to do is to consider our system, some kind of a spring hanging with some type of a mass attached to it, and develop a model that will explain how this mass bounces up and down if it's moved out of its equilibrium position. Okay, we want to know where is that mass going to be at any point in time after you, for example, pull it down, or if you push it up and let go of it, it's going to drop down and then start bouncing. Okay. In order to model this, we're going to use a second order differential equation. And the way that we're going to go about this is by starting off with a fairly simple formula that you're familiar with. Force is equal to mass times acceleration. We're also then going to define U of t as the displacement of the mass. This is going to talk about how far down or how far up do you initially pull the mass down or push the mass up. Okay, since u is a displacement, it's a position. If you recall from calculus, the first derivative is going to give us a velocity. And the second derivative of this function u is going to give us an acceleration. Okay. Notice that u is going to be a function of time. Okay, so what does this have to do with force equals mass times acceleration? Well, we can rewrite our force equals mass times acceleration, replacing acceleration with u double prime, or the second derivative of u. The force itself is going to be defined in terms of time, position, and velocity. So this function that we're going to wind up with for force is going to have the variable t. It's going to incorporate the position of the mass, and it's going to incorporate what type of velocity is introduced to that mass. This then gives us an equation where we have m times u double prime, the second derivative, is equal to some function that involves u, u prime, and some type of a constant t. Okay, so we want to take a look at the forces that can act upon this system. And there are going to be four that we're going to look at. The first of these four forces that we're going to consider is gravitational force. We're just going to refer to that as F sub g. Okay, that force is just the mass times the gravitational constant, whether it's at 32 feet per second squared or 9.8 meters per second squared. The second force that we're going to consider is the spring's force. We will refer to that as F sub s, S for spring, and we're going to depend on Van Hook's law. This works well for springs, provided that you don't have excessive stretch applied to the spring. Essentially, what we're going to have is that the force of the spring is equal to a spring constant, K, times capital L plus U. Now recall capital L is the elongation. In other words, how far is that spring pulled down when you hang the mass on it? U is going to be what type of a force is applied to that mass. Maybe we're going to press down on that mass, which is going to cause the spring to elongate either further, or in some cases you may walk over and pick up the mass, in which case there will be less force applied by the spring. It's important to notice here that this spring force is a negative value. The reason it's a negative value is, remember, forces moving in a downward direction have a positive value. The spring is pulling it up. That's going to be moving in the negative direction. Okay, now this spring constant K is going to be greater than 0 when the spring is stretched. Okay, greater than 0 times its negative is going to ensure that the force is negative or moving upward. Okay, when it's in equilibrium, we're going to have F of S equals negative KL. It's negative, just like I said, because the force is acting upward. If the spring is stretched further, okay, we're going to continue to have a situation where L is some amount that it's pulled down, U is some amount that it's pulled down. Both of these pulls are pulling downward, so they're both positive. So we're going to have a constant K, which is positive, times a constant L plus a constant U. All three of these are positive, so it's going to be positive times the negative, which makes sense that the spring is going to be compensating for all of these forces applied. So the spring is going to be pulling back up in the negative direction. It is also entirely possible that you can have this change sizes. You can have a situation where you have some mass and you push up on it. Now, if you push up on it, it's going to cause this spring to compress. And as the spring compresses to a length that's shorter than the natural length, the spring is going to want to push back down. Okay? If the spring is compressed, what's going to wind up happening is the force of the spring is going to be in a downward direction, a positive direction. Now, if it's in a positive direction, that's going to change things up a little bit for us here. Okay, there are two situations. One, the first of these is that the amount of force that we apply is smaller than the elongation. Okay, so the spring elongates. What winds up happening is you have U plus L greater than 0, multiply it by the negative K, so our force is in an upward direction pulling. Okay, you can also have a situation where U plus L is less than 0. This would be where U is in a upward direction, a negative direction, and what you have then is like what I was just talking about, where the spring is compressed, it's pushing downward, it's going to wind up giving us a positive because it's pushing downward. The force of the spring will be positive. Okay, hopefully this makes some sense to you. The third force, and it's not a force that we're going to include in the first problem that we're going to look at here, is what's called a damping force. It may or it may not be present. Okay, the force of damping is going to be, notice here, the first derivative times a constant, where that constant is positive. Notice we have negative times the constant times the velocity. It's very important to keep in mind that the damping force will act in the opposite direction of the current motion of the mass. Keep in mind, thinking back to the shock absorber, if you hit a speed bump, it's going to push the tire and that whole suspension system up. The shock absorber is going to want to fight or prevent it from going up, so it's going to press down. If, however, you run over a pothole, the tire is going to want to drop down into it, and the suspensions are going to want to drop down, but the shock absorber is going to resist it dropping down, so in that case, it's going to be pressing upwards. So the damping force is always going to act opposite of the current motion of the mass. The idea is the damping force is going to try and prevent the mass from moving further. It's going to try and keep it in its natural position, okay, or its equilibrium position. A fourth type of force is what is referred to as external forces. They include other inputs to the system like friction and things of that nature. Okay, so what we can do here is we can rewrite Newton's second law, okay, and what we'll wind up with when we include all of these forces, all four types of forces, is we're going to have the mass times acceleration. Remember, this was mass times acceleration equals force, but we have four different types of force on the right-hand side, all of which combine to give us the total force. Those forces are the force due to gravity, the force due to the spring, the force due to a damper, and the force due to external situations, external being outside of the spring and the mass itself. We can take and we can rewrite this. What I'm going to do is I'm going to distribute this negative k times the L and times the U, and then I'm going to move all the terms with U or U prime to the left side. On the right side, it's going to leave us with the mass times gravity. It's going to leave us with k times L, which is going to be right here, and it's also going to leave the right-hand side with the f of t. On the left-hand side, we're going to have, oh, look at this. We're going to have mass times the second derivative plus this damper coefficient times the first derivative plus the spring coefficient times the position. Hey, this is a second order differential equation. When the mass is at rest, when it's not bouncing around, you have a situation where the mass times the gravity is equal to the spring constant times the elongation of the spring. It's really interesting here because if these are equal, what that's telling us is that the mass times the gravity minus that, well, they're equal, they're going to subtract off. No kidding. So two of these terms on the right-hand side are going to subtract off, and the equation now becomes a second-order differential equation where all that we have remaining on the right-hand side is the external force. In addition to this second-order differential equation, as it is right now, it's non-homogeneous because we do have some type of a function on the right-hand side. If the force from the outside was zero, as in there is none, it would be a homogeneous equation. That would be nice. Okay, we're also going to have some information about the initial values of this system. We will be given the initial displacement from equilibrium. Okay, how much elongation do we receive or measure? And the second thing we're going to be given is some information about initial velocity, the first derivative. Let's start with the least complicated system that we can look at. To make this system as uncomplicated as possible, the first thing we're going to do is we're going to assume that F, external forces, is none. There are no external forces. So that makes the right-hand side 0, which gives us now a homogeneous equation that we're dealing with. The second thing that we're going to do is we're going to assume, whoa, look at this, it's undamped. There is nothing here to absorb or slow down the up and down motion of the mass when it's moved from an equilibrium position. If it is undamped, that says that this damping force here is also going to be 0. And when we substitute in 0 for that damping force, 0 for the external force, what we wind up with now is an equation like what we have at the top of the screen. We have mu double prime plus ku equals 0. You know how to solve this. This is one of those situations where we're going to do the r squared plus something or other r plus some constant equals 0. Oh yeah, characteristic equation. That's how we solve these. And what we're going to do is we're going to go ahead and we're going to set this up by solving to find what our roots are always going to be in terms of some of the constants. That'll make our life easier so we don't have to keep resolving. We'll just substitute in the values of the constants, and that'll give us our roots. Remember, what we have here is a quadratic. So we could really rewrite this. Here, let me rewrite this for a minute as mr squared plus 0r plus rk. Okay, so we could write it like that. Now, this is going to be A in the quadratic formula. This is going to be B in the quadratic formula. And this is going to be C in the quadratic formula. And over here to the right, you can see I've substituted these values in for the roots. Okay. What we wind up with is R is equal to negative of B. Well, B is our damping coefficient, that's 0, plus or minus B squared, well, that's 0, minus 4 times A, well, that's our M, times C, that's K, that's our spring constant, M's our mass, of course, all divided by 2A over 2M. Okay, so we can do a little razzle-dazzle here with the algebra. And what we're going to wind up with is R is equal to plus or minus I. Why I? Because we have a negative 4mk. And that's going to give us 4mk over. Now, I could leave this denominator as 2m, but notice what I did here. I rewrote it as the square root of 4m squared. That's the same as 2m. But by rewriting it as 4m squared, This allows me to then include the numerator and the denominator within a common radical, which allows it to be simplified, and we wind up with our roots are going to be plus or minus I times the square root of k over m. Okay. Typically, this square root k over m is defined as omega 0. You can see it right there. Okay, and that's how we're going to reference it. So our solutions to our characteristic equation are going to be plus or minus omega 0 I. Knowing now what we have in the way of a characteristic equation, we can write down the general solution, which is going to give us this. Recall that U of t is going to be how much external force is applied, okay, to the mass, and winds up being this C1 cosine omega 0t plus C2 sine omega 0t. I'm going to reference this later as equation 1. All right, so without going back through and turning this into a trig class, using a trig identity, this can be rewritten. Equation 1 can be rewritten as r times the cosine of omega 0t minus delta. This I'm going to refer to later as equation 2. R is important. R is the amplitude. The amplitude talks about the up and down distance from the natural resting point of the system. Okay, delta is the phase angle or the phase shift of the displacement. So what we're going to wind up with here is our amplitude times the cosine of omega 0. Remember that was just defined for us right up here. Right there it is. It's the square root of k over m minus delta. Okay, so let's take a look at what's going on here. We have our u of t defined either as equation 1 or equation 2 towards the top of the screen you can currently see. Okay. Using u of 0 and u prime 0, in other words, the initial values, we can compute C1 and C2. Okay. And at the same time, I'm going to rewrite equation 2 using another trig identity to get this. So what I'm going to end up with are equation 1 and equation 3. But keep in mind from equation 1, we know a value for u0 and u prime 0. We can go ahead and compute those. Okay, so what's this going to get us anyway? Well, what I'm going to do as well is I'm going to keep in mind, hey, I can compute my C1 and C2. My C1 equation, which is right at the top, is C1 cosine. You can read the rest of it. And down at the bottom here, hey, they both fit. I want to compare this equation with this equation. Now, by comparing, that means in the first term, both of them have this cosine right there. That then means that r times cosine of delta is going to be this C1. Similarly, for the second term in my equation 3, I'm going to wind up there with r times the sine of delta is equal to C2. All right, so that's helping us move along here a little bit. So we have C1 is equal to r times cosine of delta, and we have C2 is r times sine of delta. From this, we can take C1 and square it, C2 and square it, and if we add those together, and you may be thinking, oh, well, what's that going to get me? Watch what happens here. If we square C1, we get r squared cosine squared. If we square C2, we get r squared sine squared. You may have spotted something. On the right-hand side, we can factor out the r squared. This leaves us then with C1 squared plus C2 squared equals r squared times cosine squared plus sine squared. That should ring a bell. Cosine squared plus sine squared is 1. This gives us then that C1 squared plus C2 squared equals r squared, or if we take the square root, it gives us that r is c1 squared plus c2 squared. Take the square root of that. And we're going to assume that our amplitude is positive. So this r value, this within this box here, is our amplitude for our system when we take and we move the mass out of its natural resting position. Okay, next thing we need to do is we need to compute delta. Delta, how do we get delta? Well, if we take C1, which is up here at the top, and C2, which is up here at the top, both of them in this box, and we form a fraction. See down here at the bottom, now be careful, I did C2 over C1. There's a reason for this. And that reason is it gives us the sine divided by, well, I've made a mistake here writing the notes, divided by cosine. In this fraction, the r's will cancel. And what we have is sine over cosine. Oh, that's tangent. So this gives us then that C2 over C1 is equal to tangent of delta. If we want to solve for delta, we just take the arctan of both sides, and this gives us our phase shift or our phase angle. Important to keep in mind this is an angle. Okay, this angle is going to be the arctangent of C2 divided by C1. Well, that's a whole lot of really cool math, but how on earth do we actually use this? Let's take a look at an example here. Okay, we're told that a 12-pound weight elongs a spring by 2 feet when it's attached. Okay, so we've got a situation where we have a spring, and when we attach this 12-pound weight, be careful, notice this is empirical, so we're going to have to convert that to a mass. Okay, it stretches it so that we had our original position this much, and when we hang that, it stretches this down to the center of mass this much, and this additional amount of stretch is 2 feet. So that's what that's saying. There's no damping, no external forces. Aha. So that is going to allow us to simplify our second order differential equation considerably. We're going to get to drop 2 terms. Okay. As we read on here, the mass is displaced upward 6 inches from equilibrium. Now be really careful here. 6 inches, I need to take this and I need to convert this to feet so I have the same units. This is 1/2 of a foot. Okay, so what's going to happen is this mass is going to be pushed upward 6 inches, and then from there it's going to be given a downward force or velocity of 1 foot per second. Okay, so the question then is, what does the displacement at any point in time look like? Displacement means how far is it from the resting or equilibrium position at any point in time. That displacement is u of t. All right, so we've got quite a few steps to work through here. We're going to go back through everything that we just talked about and stick some numbers in. First thing we need to do is we need to convert this weight to a mass. Well, recall that mass is equal to weight divided by gravity. So our mass, I'm not going to drag along all the units here. Our mass is going to be 12 over 32. Well, there's a 4 common to both of them, 3/8. There is our mass. Don't want to lose that. Okay. Second, we want to compute K. Well, we know that K times L equals M times G when this thing is in a resting position. This gives us K is equal to mg divided by L. We just computed the mass, that's 3/8. The gravitational constant is 32. L, the amount the spring is displaced, is 2 feet. Notice it's 2 in the denominator, not 24 inches. All right, so this, when we simplify, gives us that K is 6. We have M is 3/8. The next thing we're going to do is we're going to set up our initial value problem. Since there is no damping, this term is gone. Since there are no external forces, the right-hand side is 0. Okay, so this can be rewritten as this equation right here. M times u double prime plus ku equals 0. We know that the m is 3/8. We just computed that. And the k is 6. So we have our two coefficients, like that and like that. Okay, recall earlier where we solved for our roots for our characteristic equation and came up with omega, which is going to be the square root of k over m. And if you look back up in the notes, remember k is 6, here it is, and m is 3/8 right there. So we take these two values and we substitute them in. 6 divided by 3/8, the square root of that equals a very nice 4. If you refer back to our equation 1, this will allow us to write our general solution. We're going to have C1 cosine of 4 times t, the 4 being this omega, plus C2 sine of 4t. We can also take the derivative of this, which is going to give us negative 4c1 sine 4t plus 4c2 cosine 4t. Why do we want to take the derivative? Well, recall we're given two initial pieces of information. One of those being its position, the other being its velocity. Oh yeah. So what we're going to do here is we're going to take u of 0, and u of 0 was a negative 1/2, and we're going to set that negative 1/2 equal to the C1 cosine 4 times t, C2 sine 4t. But remember, since it's at the initial value, our t is going to be 0 in each case. Now this is going to make it pretty nice because the sine of 0 is 0, the cosine of 0 is 1. So we get then that C1 is a negative 1/2. Now remember, be really careful here on this initial position. Remember we were told it was lifted upward. Okay, so the negative is because it was lifted upward, and it was lifted upward 6 inches, which is a 1/2 foot. So that's where the negative 1/2 comes from, giving us our value C1 is a negative 1/2. Using the derivative, which is at the top of the screen, I'm going to substitute in 0 for t, and we know that our initial velocity is 1 foot per second, so that gives us our left-hand side here. Substituting in 0 for t, our sine once again winds up being 0, and we get 4c2 times cosine of 0, well, cosine of 0 is 1, allows us to then determine that C2 is 1/4. Substituting in C1 as a negative 1/2, C2 is 1/4, gives us a general solution now. We're making progress. The next thing we want to do is to compute the amplitude R. Well, the nice thing is we already know what C1 and C2 equal. C1 is this negative 1/2, we're going to square it. C2 is the 1/4, we're going to square it. When you square those two, add them together, you get 5/16. Square root of that is about 0.559. The next thing to do here is to compute our phase angle. Okay. And if you'll recall, that value for delta is the arctangent. Be careful, it's C2 over C1. Be real careful to notice that. Okay, people are inclined to do C1 over C2. That won't get you where you want to be. So we're going to do the arctangent of the C2 value, 1/4, divided by the C1 value, a negative 1/2. And when you compute that, you get the arctangent using radians is a negative 0.464. Now, this is going to wind up being in the fourth quadrant. Another possibility is this angle could be in the second quadrant. I wonder which it is. Well, what we're going to wind up doing is we're going to say, okay, we're going to use our negative 0.464 as delta 1, which is now at the top of the screen. Delta 2, which is in the second quadrant, is achieved by taking delta 1 and adding pi. That works out to be about 2.678. Okay, so the question is, which angle do we use? We've got two angles, we can only go with one of them. Okay, let's think about what's going on here. When we substitute in our delta, the cosine of delta has to be the same as the sine on C1, S-I-G-N. Okay, if we come up here, somewhere up here, way up here, where'd it go? Dun, 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 dun. Yeah. Let's see here. Okay, the sign on the C1, oh, the sign on C1. C1 is negative. Okay, C1 is less than 0. Remember, it's the negative 1/2. So the cosine needs to come out being a negative value. And the sign on the SIGN on the sine of delta has to be the same as C2. Well, C2 is positive. If we have our cosine negative and our sine positive, that has to be in the second quadrant. So the angle that we're going to want to work with is what's in the second quadrant, which is going to be this 2.678, delta 2. Okay. Where's that leave us? Well, where that leaves us now is that we have our equation, okay? U of t is going to be r cosine of omega 0 t, okay? Omega 0 t minus delta, substituting in the value for r, 0.559, and the value for t or delta as 2.678. The omega was 4. This gives us our equation. Now, one of the things I want to point out to you is you can graph this on your calculator. You can just set this as y equals, and remember, u is the position. How far has the mass moved away from its equilibrium position? And it won't move any further away than what the amplitude allows, because cosine's largest value is 1, cosine's smallest value is -1, so it can only move either up or down away from the resting position at most by 0.559 feet. It's a little over 6 inches. Okay. If you graph this, you can see that. And when you graph it, you're going to want to set your range on y to be from -1 to +1. Now, the nice thing about this is, now that we have this equation, a real fair question could be, well, okay, so where is this mass going to be 3 seconds after the system starts? You just substitute in 3 for t, and it gives you a height, either above the resting position or below. Well, I hope this makes some sense to you. Take care.